My name is Oshuda, and today I will talk about the topic is linear transformation. These transformations are not only powerful tools in pure maths, but also essential in applications such as computer graphics, physics, and engineering. Let's begin by looking at some basic geometry transformation to build our institution. Many common actions in geometry, like rotating a shape, flipping it over a line, or sliding it to a new position. All these are geometric transformation, and many of them can be described using linear transformation. So, rotation, refraction, and translation are all examples of transformation, and these transformation change the position or orientation of shape in space, but often without alternating their size. This leads to a key question. Can we represent this transformation using algebra? The answer is yes. And that's actually what linear transformation do. They use metric multiplication to perform geometric action. Then in linear algebra, a linear transformation is a mapping between two vector spaces that preserve the operation of vector addition and scalar multiplication. A transformation T is considered linear if it satisfies these two properties, the additivity property and homogeneity property. Then, and these two properties of a linear transformation can be used in combination. So we can say that linear transformation preserves linear combination. Now we look at the definition of matrix. This is a construct about the M times matrix. And we look at the definition of matrix addition and multiplication. This means matrix can be add and subtract item by item and multiply by number. Now we look at the definition of matrix multiplication. This means it is a row by column accumulated operation. Then we identify X with the column vector, which is a M times 1 matrix, and A is a M times N matrix. Multiply it, we get a new vector Y. Then the result of the vector is the dot product. The ith row of A dot with X. In short, multiplying a matrix by a vector performs a linear transformation, combining the vector component with the row of matrix. So we have seen that when a matrix is multiplied by a vector, a new vector is obtained. This process is what we call linear transformation in geometry or application. Then, can we ask the opposite question? Can any linear transformation be expressed as matrix multiplied by a vector? The answer is yes, and the matrix is unique. This is extremely important theorem, the correspondence between linear transformation and matrix. Now we look at this theorem. A function T is a linear transformation if only if this exists and M times N matrix A such that Tx equal to X. In this case, A is called the matrix associated to the linear transformation. So every linear transformation is equivalent to a matrix. The row of the matrix is perform this transformation. Now that we have defined how the matrices are on vector, such as Tx equal to X, so we can formally establish a very important two-way connection proof. We start with a transformation defined by a matrix, and we find that it is automatically satisfied two key conditions of linear combination and linear transformation, the addition and multiplication. So we're proving that T preserves these two property. Then since T preserves these two property, then therefore any transformation defined by a matrix multiplication is linear. Conversely, we start with a linear transformation and want to find out whether it can be represented by a matrix. We decompose the input vector x into a linear combination of standard basic vector and use linearity to distribute the transformation effect. as long as we know that the result of linear transformation on the standard basics, we can construct it to a matrix form. This means that every linear transformation T can be represented by only one matrix A, satisfy Tx equal Ax. Linear transformation distribute over vector addition and scalar multiplication, so it can apply T to any linear combination of vector. For the linear transformation T, then this is a component function for T1 to Tn. Each of them is a polynomial of degree at most 1. Thus, a linear transformation is polynomial mapping of degree at most 1. It is easy to deduct the following thoroughly. The mapping T is a linear transformation if and only if each component function is linearity transformation. Now that we know how linear transformations are represented by matrix, so the natural question arises. When is a linear transformation invertible? In a particular case, when m equal to n, we have these two theorems. The first theorem is the four equivalence statement for the mapping T is 1 to 1 and onto. Then the matrix A is invertible and the determinant of A is not equal to 0. So for this outset theorem, we can show in the linear transformation. Let T be an invertible linear transformation represented by the matrix A, then the inverse mapping for T is also linear transformation. Then we get the inverse mapping is equal to A inverse matrix multiply X. So we know that the inverse of linear transformation is still linear. Now we saw some example about this theorem, this old theorem. Then consider the linear transformation T from R3 to R3 defined by this equation. The first question is find the matrix represent A of T. We can substitute the standard basic vector E1 to E3 into T, the result in the column vector of A. So we have the column vector of A, then we can construct to the matrix A. The second question is we can verification of linearity with component function. We aim to verify each component function of T is linear transformation. We just verify the linearity of each component function Ti using the definition above. So using these two property, then we verify it. Then we show that all component function T1, T2, T3 satisfy the linearity condition. Means each component function is linear transformation. The third question is determine if T is invertible. Determine whether the matrix A is invertible, whether we just show determinant A is not equal to 0. Compute the determinant A, we get the result is negative 33. So it's not, since it is not equal to 0, so T is invertible. And the last question is if T is invertible, find the matrix A inverse and compute the inverse mapping with the point 1, 0, negative 1. Then we first need to show the A inverse matrix. So we compute the cofactor matrix. Then we have the A inverse matrix. So by the theorem 4, we show that the inverse mapping is A inverse matrix multiply X. So we multiply this point 1, 0, negative 1, then we get the result. So this is all about my topic linear transformation. Thank you.